Roth here at the IAC, who I've been collaborating with since 2017, is a nice consequence of one of his previous visits to the IAC. Professor Roth had his PhD in astrophysics at the LMU in Munich. And then during the PhD was very much involved with FORCE and the ISO detector lab. And then since 1994, he has been the head of the instrumentation in the IAP in Potsdam, where he actually started the instrumentation group. And his major projects have been PMAS, MUSE, and Blue MUSE ongoing. Since 2011, he has been on a joint professorship between the IAP and the University of Potsdam. And then since 2023, he's a emeritus professor. Since then, he's a full-time staff astronomer at the IAP. And now he's the head of the emerging, I should say this in German, but I'm not going to do this. So the German Center for Astrophysics Institute of Technology, which will be the main topic of today's talk. Thank you.
Muchas gracias, Giuseppina. Primero, en mi pobre español, bienvenidos. Y es un placer estar aquí, un lugar querido en mi corazón. Hace muchos años, y Jesús me dijo, después del año de 2002, ¿no? Y más antes también, and I'll stop here, otherwise I will fail with my Spanish. It's wonderful to be here, and thank you for the invitation to give a talk on something that after my retirement a year and a half ago, has occupied my attention. I'm still working at the Leibniz Institute for Astrophysics, and this is the DZA, unspeakable, as you just said, the Deutsches Zentrum für Astrophysik, which is emerging in a little place known to only a few people, Görlitz. And this is going to occupy maybe half of my time. I understand I have 45 minutes, that's all? Yeah, thank you. And the other will be concerned with more of science, and all of this is geared very much towards the future. So this is not operating well. So anyhow, let me get started. Yeah. Oh, oops. Little glitch. Yeah, the batteries have failed. So let me just start out anyhow. This German Center for Astrophysics is something that I would consider follows the IAC as a role model. As you probably know, in Germany, we have Max Planck Institutes. We do have Leibniz Institutes. We have university departments active in astronomy, but we don't have a national research center. And as it happened, I don't need the laser. It's the forwarding the slides. I'm sorry for the technical hiccup. I will just exit from Zoom sharing and start again. The classical switch on, switch off seems to work, so never mind. What you see here is a landscape of, on the right-hand side, Poland, Czechia, Prague on the lower side, and the eastern edge of Germany. Maybe you recognize Dresden. And then you have this little city of Görlitz, where we are planning to install the German Center for Astrophysics, DZA, which will also have, and I will talk about this a little bit, another lab, an underground lab, in fact, in the vicinity, which will have to do with gravitational wave astronomy. Anyhow, why is this happening? You probably wonder why I'm showing enormous equipment for coal mining. Well, we have legislation in Germany saying that this has to stop. But never mind, it works this way. Thank you. Can use the pointer. We have legislation in Germany since 2020 that because of global climate change, we stop coal mining and have a conversion to renewable energies. And to facilitate this, because obviously there will be unemployment when companies have to close, the German government has set aside 40 billion euros for the transformation process of the economy. And the local state of Saxony has decided to set aside 1.4 billion euros of that to create a research center, actually 2 of those. And they made a competition, and 2 have won out of like 100 applications. And miraculously, Astrophysics won one of the 2. And this is the origin. It's not funding from science, it's funding from economy that goes into the creation of the new Center for Astrophysics. And perhaps it will become apparent why this is hoping to work in the transformation process. And what I'm showing here is in the inner part of this collection of portraits, the 9 people who have actually developed and submitted the proposal. And the designated founding director, Günther Hasinger, is shown on the left upper side. He is now retired, the head of science of ESA, and moved to Görlitz. And then there are a number of other directors of institutes all over Germany who have condensed their ideas into that proposal that was successful in the end. And further people now helping to the steering committee to actually install what is going to, with the interests of those initially engaged, focusing on 2 major research lines that have to do with gravitational wave astronomy and radio astronomy, requiring more massive investment and development power than a single small institute would have. And this is why I say the IAC, in a sense, is a role model for that initiative. And well, the goal is to be able to participate in major international collaborations of this sort. So this concept will further evolve. But anyhow, the concept is to have 3 pillars for the future DZA, namely 3 institutes, one focusing on astrophysics, this is the left pillar. Then in the middle, this is my task, build up an institute for instrumentation, actually technology development at a larger scale. And then, and as you probably appreciate from radio astronomy, but also massive surveys that we're looking forward into the future, big data processing. There are big challenges ahead. So these are the 3 pillars that will form the DZA. And a bracket, and I'm glad that Isabina is arranging a visit to IAC Tech, another role model for us, technology transfer, is part of this whole concept. Now, I have to do a little bit of pretty pictures in astronomy. You are well aware of the center of the Milky Way, such as a star. And well, just if you focus on that field, which is 2 degrees across, and then, well, this is just the degraded image of that previous amateur photograph. And you look into the radio, this is a compilation of America data, which I thought I have to show. It's just too pretty to imagine. So here's such a star. Very well, it was known and found as a radio source, of course, but a number of known supernovae remnants, etc. But this is the arc whose physics is not understood. It's several kiloparsecs across and very fine structure, amazing. I mean, this is what I, just for the fun, wanted to show, and leading to, again, pointing to the motivation why radio astronomy is amongst the topics of interest. We have very strong support from the Max Planck Institute for Radio Astronomy in Bonn, as you may have heard, took a long struggle to convince the government that Germany can enter the SKAO, which is now happening. So this is kind of indicating the area of interest, why that topic should become a research line. And in fact, DZA is receiving already substantial funding in a startup period. And we are looking forward to receive 2 Meerkat mirrors, actually complete telescopes. As you see here is a prototype, a first version that is a development for SKAO from Bonn after installation in South Africa earlier this year. And I can tell you just in August, I was attending a factory acceptance test of one of the two telescopes that we will receive on our budget for DZA for that same America type of radio telescope here in the factory where they are contributing most of the telescopes for SKAO. Now, I'm not an expert in gravitational wave physics. This is just an advertisement sketch of, you look at the scale of frequencies that are covered of follow-up for LIGO Virgo, the Einstein telescope, and then, of course, DZA and Pulsar timing arrays. This is the kind of science that is of interest to those people who are driving DZA. But what this has to do with the planning for DZA is shown in this slide, where the idea is to, in the region that I was showing on the map already, create an underground laboratory. That would be a place where you have, because of the existing slab of granite, which is the largest extent found in Europe, 20 kilometers across to a depth of several hundred meters, very stable conditions. You know, some of the best optics tables are made out of granite, and that is a huge optics table underground. And the idea is to maybe 100 or 200 meter below the surface have this lab. This is an artist's sketch where those columns show cryostats cooled to 4 Kelvin to have noise-reduced mirrors mounted for the interferometer that will be used for the Einstein telescope to achieve the new generation of sensitivity. This is an amazing technology. This is beyond my own appreciation, but this is what is going to be built in the next 10 years and also become perhaps an entrance fee for a possible location of the Einstein telescope. There are competing ideas around, but this is going to be, I guess, selected in the next few years. The reason why I was pointing out technology transfer, of course, such a lab would be fantastic also for very, very sensitive experiments of future technologies like next generation lithography for microprocessor chips or microscopy and so on. So this is a vision that is also stimulating the transfer and transformation in the region that will stop coal mining. And therefore, politicians have been keen to adopt it. Okay. Ah, you have to shake it, then it works. Never mind. Okay, a second topic that is dear to my heart has to do with the region around Dresden that is known for semiconductor industries. It is one of the European centers for this kind of technology. And as we all know, detectors are important elements of our telescopes. There is no point to make a GTC if you have a low quantum efficiency detector on it. And since we are worried that, and I know that ESO is very worried about that, CCDs may no longer exist in 10 or 15 years for the long-term development, this is an area where we want to engage. And we're actually talking to Fraunhofer institutes in Dresden. We're talking to ESO. As we speak, we are actually building a lab in Görlitz. So this is one other area of technology that we want to engage in. CMOS is a buzzword that plays a role in this context. I won't go into all the technicalities of this, but just point out that this is going to be happening rather soon already. Now, this is a busy slide, and I have inherited just to focus on two things that we also want to do very soon. Here you see a radio receiver, which is a sophisticated technology involving a cryogenically cooled antenna and then very sensitive electronics to pick up the radio signals from the dishes. This has been developed for Mekat in Bonn, and the plan is together with an industrial contractor, OHB, to actually involve mass production of such receivers that will be needed for the SKAO. We're talking not about 5 or 10, we're talking about 64 or more. So this is what we're actually planning to install probably next year in the electronics lab that we're building up at the present time. And the other thing that is really not easy to sketch here is, let me say that in words, a technology needed for those interferometers of the next generation for gravitational astronomy Currently, they're using quartz mirrors, massive quartz mirrors, but the next technology needs crystals made of silicon. And this is what semiconductor industries use for their wafers, with the current technology of 300 millimeter wafer, this size. But now the goal is to grow this to 600 millimeters. This is a tremendous challenge. This is another area of activity that, in collaboration with the rest of the gravitational wave community, what we want to address in the forthcoming future. So the third pillar that I was introducing, big data, has to do with the massive data that will be coming out of the SKAO. And just to focus on this thing, because this we were talking about integral field spectroscopy. This is a data cube in the radio. Well, data cubes were invented in the radio in the first place, but this would be a petabyte for a single object. So it would be like 1,000 of our laptops capacity. So storage, online processing, offline analysis, this is a tremendous task. And this will also be addressed by the DZA in collaboration with the Technical University in Dresden, where they have already competence in their research center. Okay, and then perhaps I should skip this advertisement of what the sizes of data chunks are. And this is coming. Have you heard of brontobytes? I know of brontosaurus, but anyway, let me skip that and just tell you, this is, I mean, the future picture, but to convince you it's happening. 2 years after the announcement by the minister, federal minister, the winner is, we do already have a provisional headquarter, which you see here. It's the previous post office in the center of Görlitz, where we have our offices, and in particular the director's office. And here you see that high-ranking politicians have handed over the key. This happened in February. And more closer to my heart, this is a provisional lab building that we are currently equipping at the compounds of a company. Here you see, again, people involved in the handover. But I just want to say, here is a map to convince you it's happening. We have 2 optics lab, detector lab, computer, etc. This is from 2 weeks ago, already the equipment that is arriving as we speak. Yeah, this is happening right now. Next week, I'll be going to receive 2 optics tables. And so we are ready to launch activities. We do have an electronics lab and more space for offices for the future growth of the center that will end up, that's the plan, on a new campus. It's a bit difficult because it's a protected area. So Görlitz is a beautiful town, but it's protected heritage. So you just cannot put a square of concrete. So you have to embed it nicely. And this is a process that will take a longer time. So for a period of like 5 to 7 years, we envisage to stay in our provisional buildings, after then move into what is called the Karlbaum area. And here I close up with saying what is now happening. We are making the procurement of 2 Americad antennas. We're establishing the data center. I've talked about silicon mirrors and detector development as the real objective of work that will start in the next coming months. And we have a number of professorships that will be filled. And the long-term development can be seen on this sketch, where you see over 15 years. This is the funding period for the mentioned 1.4 billion euros. We expect staff to complete the full number of people at the level of around about 1,000. And for what concerns my work, we expect around about 270 engineers and scientists to work there in 15 years. And we are now where the blue arrow ends in the 3-year startup phase, after which we have a formal foundation of the institute. Right now, we are not yet existing. So we're developing the government model, etc. All right. And you see, this is from a team event in June, but we have already 20 people more, and I can tell you we are hiring. Now, let me come to the second part of my talk. Half time. May I ask who in this room has heard about the Wide Field Spectroscopic Telescope project? Just maybe a third of you. Okay, then it's probably fine to say a few words about it in general. Since ESO is worried that once they have built the ELT, if there was no successor project, the organization may lose its ability to build and maintain telescopes. So Javier Barcons is going to initiate a process of brainstorming and collecting ideas, what could come next. And as a provision to this, people have formed an initiative to really start working on a conceptual design of such a telescope, survey telescope. And to motivate it, let me show you a few slides why I think this makes a lot of sense. And now I come back to what DZA just said in her introduction. I've been here 7 years ago to report on progress on a MUSE GTO program that I started at that time. A year later, we published the first paper, and this was about a nearby galaxy, NGC 300, and results solar populations. You see thousands of stars that you can extract from the data cube. And then when you go in the mission lines, Jesus knows very well what that means. You get all the gas. It's a beautiful picture observed actually now with data taken after my talk in AO. So this is full of science. I have no time to speak about it. Just mention if you're interested, you can look into those 4 papers that were published from that data set. The 5th is in the making, concerned with Therium, massive stars. Actually spawning 2 more papers, however, that were basically based on archival data, which have to do with measuring distances to galaxies based on the planetary nebular luminosity function. I would love to give a talk on that, but I have to postpone this to another time. The point I want to make is MUSE has become a very efficient instrument, efficient in terms of productivity. And if you look into this research note that I published in March, I believe it was, there is a part that is available on the MUSE website showing the number of papers produced by any VLT instrument from the installation of the facility to 23. And you see MUSE with a shooting star with more than 200 papers in 2023. This is, of course, we have contributed to this project, very rewarding. It has to do with a number of facts that I would be happy to discuss, but I want to show you what I have done. I just slipped this problem, so I had to stay at home and could not do serious work, but I actually was counting P's, and I was analyzing the ESO library data, showing all the papers. It's roughly 1,500 papers that I've looked into the abstracts and categorized them. Black and gray is high and low redshift cosmology. The blue sector is nearby galaxies. And then there's a small contribution by solar system in red and Milky Way in yellow. But this is a fraction piece of the cake that makes me very happy because we help to develop this kind of science. It's resolved stellar populations observed with the MUSE IFU. And in 2 weeks' time, there is a conference in Florence that I'm looking forward to, celebrating the success of this technique for CCD photometry. And we always had the dream, can we transform this into, integral field spectroscopy analysis of crowded fields? And this is happening, and this fraction of 11% is quite remarkable. And I have to give credit to Sebastian Kamann, who did his PhD in Potsdam, now in Liverpool, who with our colleagues in Göttingen has helped to develop the technique of crowded field, integral field spectroscopy a lot. So this is what forms some of the ideas that go into the WST proposal. But the other point is foremost. Anyone in this room attached to science with foremost surveys? A couple of you are. So we are all looking forward. It's happening. This is 3 weeks ago when we were introducing people from DZA of my team there in our integration hall in Potsdam. This equipment is no longer there. It's already shipped to Chile. So it's going to be commissioned in the very near future. Showing Muse and Foremost as two major ESO projects is the motivation, which I want to explain to you for why WST makes sense as a future survey facility, spectroscopic survey facility. The sketch on the left shows you a telescope, a 12-meter telescope, which would have in the Cassegrain focus a MOS, like Foremost, but one order of magnitude more complex. And then an integral field facility, which would be roughly 10 times the capacity of the current Muse. However, you should rather say a combination of blue Muse and Muse. It would have a dichroic beam splitter and cover all of the optical wavelength range. That's the conceptual idea. To convince you that it's not just a dream, the PI of this idea, Roland Macron, has submitted in a second attempt a proposal to the European Commission in the infrastructure call of this year, the deadline in March. And we have received funding to start a conceptual design study. Now, this is a technically very demanding project, and I point you to a paper that we have published jointly with Roland on only the problem of the detector systems. You would need like 360 or so detectors, whereas Muse has 24 and a similar number for other MOS instruments. So this is gigantic and will require a completely new approach to the technology. This is something that we want to address at DZA with partners at ESO. So this is from the technical point of view, but of course, this does not stand alone. You need a science case for this. Oh, I'm missing a slide. Anyhow, let me just say it in words. We think the combination of a MOS with an IFU is a unique capability that is really worthwhile driving with developing the science. Okay, now I come to you. Here's a paper that was published 4 weeks ago by someone who did his PhD here at ISC, Salvatore Taibi. And our collaboration started 7 years ago when, after my seminar, Giuseppina invited me to her office to show me data that she had on her computer. And she asked me whether, based on the experience that we had gained with NGC 300, I could contribute to the project. And I said, oh, this is fascinating. You can see the Roth galaxy IC 1613 broadband image, and then 3 pointings that Muse has obtained. Roughly an hour exposure time each under good observing conditions. And this is what you get when you reconstruct BVR images from the Muse data cubes. And okay, this is a bit quick. So this is the collection of the 3 fields. And now I show you very quickly a number of showcases of stars that I have, and with the help of Alexandra Batstik's library called MuseCut, which is a combination of the MILES, the classical MILES library, you know that very well, and the Indo-US library, and basically covering the entire wavelength range of Muse, which I have used with the ULIS tool to fit the observed spectra. And here's one example of a star where you see it's a blue star, B star, with rather prominent Balmer lines. You see the Parsons series, and signal to noise 23, and a radial velocity that has an error which is kind of acceptable, given the distance of their galaxies, I would say, and the exposure time. Of course, you would like to get closer than that. And well, here's another star. You can get that when you have a late type giant. This is a K star where the error bar is just 1 kilometer per second. And I can go on further with other examples. Here, this fainter star is only a signal noise of 7. Still, you get a radial velocity and a classification, by the way. Or here, this yellowish object. Who knows what that is? It's not in the library. So I was first puzzled. I thought, oh, this is very noisy. But this is, if you compare the black observed spectrum with a rebinned spectrum of high resolution with the X-Shooter library, it's a carbon star. And therefore, the error on the velocity is, I believe, real. It's practically noiseless. It's a very luminous star, actually with the luminosity function of carbon stars. You can measure distances nowadays. Anyhow, here's another object that is blue, and you see a broad emission line in H alpha and blended also in H beta. This is likely to be E star. So you even get the younger population in this galaxy. And here we have something very red. Guess what that is? This is a redshift 1-ish galaxy. And then we have something on the corner. It's still possible to extract a spectrum. And you see this is a main sequence dwarf star from our own galaxies, as you probably can guess from the very different radial velocity. So you can see that contaminating foreground stars, as opposed to photometry, you can easily spot with spectra. So this was just to motivate why I was fascinated when I had this data from DZA, and with Salvatore working on it. He made a very nice paper of it. The science is what I really would like to recommend to read. I have no time to do this now, but I would like to close with making the argument again for WST. You see, those 3 pointings are very sparsely covering the galaxy. Wouldn't it be nice to have it all? So this would be very expensive. Now, however, what I'm showing here is a total of 12 pointings of WST. So in 2 nights, you could do this entire galaxy, plus having the advantage that around the IFU, you would have the moss. And I'm learning from DZA that out to 5 or 6 or maybe 8 effective radii, you can find stars from that dwarf galaxy. So that would be a fabulous combination and actually strong argument to have simultaneous coverage from both the MOSS and the IFU on this future telescope. Now, here is the result of a number of working groups that have contributed to the white paper that I encourage you to find on the archive. It was published in March. And it turned out at the discussion where you had basically Milky Way, nearby galaxies, and cosmology, that the subject that we were discussing and proposing, results stellar populations, would not really fit into either of the categories, neither Milky Way nor cosmology, nearby galaxies. So it was decided to have its own working group. And I'm very grateful that DZA contributed a lot. Artemio Herrero, I think, who's not here today, also did. So we have a number of IC people here on the total of, I believe, more than 200 co-authors who have really contributed to this first step into defining science for such a future project. And I'd like to tell you, this is not a closed shop. Since we have now, and this is a little bit analogous perhaps to MSE, which is having its problems on Hawaii, we want to improve on that white paper. And during the conceptual design phase, we will resume further discussions with the community and ask people who are interested to contribute. So it's not, even though there is already a consortium forming for doing the technology development of the telescope with funding from the European Union, this open process of involving the community is really encouraged. Yeah, and if you look into the table of contents, you will find that extra section on results stellar populations. And my last slide here shows basically, and I started out in my talk with saying this is very much projection into the future, that the facilities that we expect for the next 30 years, so not for my time scale, some of the facilities I may be able to see in my rocking chair in retirement, but some of you, the younger ones, are probably looking forward to use those facilities. James Webb is there, Gaia is there, etc. But WST would be pretty much on the timeline of future facilities, in particular, the synergy with the Einstein telescope and SKAO is something that is worthwhile discussing at depth. And another point that I had no time to discuss is the time domain. That was also a very important point of the white paper. So this is where I'm at the end of my presentation. Thank you for your attention. And if you have any questions, I'm here to answer.
Thank you, Martin, for the very nice and comprehensive talk about the future. And so any questions and comments in the room?
Hi, very, very nice talk. Thank you. I was just wondering, you said that cosmology was among the three branches, the three topics in astrophysics to be pushed forward in your new institute. I was wondering within cosmology, which fields which collaborations, which I've seen Torsten Ensling as one, as probably the cosmology leader, right? But he's doing also already astronomy, so I don't know which of the two branches he's going to lead or he's going to push forward, maybe in both. But my question was, what do you want to do in cosmology? Inside cosmology, you want to push SKA, you want to, just wanted to know, are you going to get involved in CMB experiments, future CMB experiments, or what's your idea about this?
So the answer to this question is we are hiring. I mean, we have to accept the fact that this is not an institute that exists. It's in the making. So we have a core team of enthusiastic people, however, who have their, commitments in other institutes. I'm only contributing 50% of my time to the ITE, and this is similar to of my other colleagues. So when I was very shortly showing what we are going to implement, there was a slide with the projects that we're going to go into, and then also the professorships, we are expecting that we attract also enthusiastic people who drive that science. And that would in particular concern cosmology, I would say. Torsten, I'm actually scheduled to a Zoom meeting with him to discuss aspects of data analysis of data cubes and finding the needle in the haystacks. And he's an expert on data analysis with advanced techniques. So, but this is perhaps not a major driver in terms of surveys. Yeah, we would need, competent people who are keen to do that. And from my own experience, I can tell you this. I arrived in Potsdam in 1994, and the institute that existed was very well known to having made MHD models for the creation of the solar dynamo and other theories, also a little bit in cosmology, but nothing in terms of instrumentation. So it was very hard, but it was possible. We started out with PIMAS as the first real instrument, then moved to Muse, and now I have shown you from our integration how Formos is being, and AIP being the PI of that instrument, being assembled and commissioned. So this is a development, and I hope we can make the site in Görlitz attractive to, on a similar line, develop ideas. So if you're young enough, if you're enthusiastic, and if you acknowledge that there are very significant resources to hire people, to engage in projects, then this is a fantastic prospect, in my mind.
Sure, thank you.
More questions?
Thanks very much for the talk. My understanding is there is a social component to the decision to make this huge center there, right?
Yes.
So are there any plans? Obviously, the existing expertise there is very different from what is required to sustain these large scientific facilities. Are there any plans to actually align the existing expertise currently present in the region to the requirements of these facilities?
Thank you for this question. This is exactly my job. We are actually having a person who is responsible to develop transfer, and his name was shown on the portrait page. Jürgen Besold is professor, retired professor at the Rossendorf Institute in Dresden. And he has basically created a startup center and worked out many connections with companies in the area. And we are constantly speaking with companies. So this is a very important element. And as for myself, with regards to detector development, we're talking to the Fraunhofer institutes that have all the technologies for wafer fabrication. And right now we are in the process of discussing CMOS developments, which are the next big step in astronomy as far as visual detectors are concerned. Something that is not known in the community yet is, you perhaps have heard of OLEDs. This is the technology that is probably now in your smartphone, making the display organic semiconductor LEDs. An LED is a light emitting diode, but you can also make a photodiode, right? So to use organic semiconductors for detectors is something that we want in collaboration with the main inventors of OLEDs in Dresden to implement also in that center. And you're quite right, since the budget is not coming from the BMBF, the Federal Ministry for Science and Education, so it's not research money per se, it's from the economy ministry. This is the major motivation. And the Prime Minister of Saxony is very aware of this and is still very much supporting it.
You mentioned time domain, and LSST is about to start, as you know. So 10-year survey, a lot of transients, thousands of supernova per night, very few telescopes to follow up spectroscopically. So I think an issue in astronomy these days is medium-sized telescopes with a spectroscopic capability, robotic telescope, like the new robotic telescope that is being planned. So have you thought of that niche?
Well, I fully agree with what you're saying. I mean, that there will be a huge demand for this new emerging field in astronomy. And of course, this one facility will not be able to cover everything. It will be reserved for the fainter objects. I am not an expert on compact objects, but as you, I read the paper about kilonova explosion and the science from that, and nuclear synthesis that is important for the chemical enrichment of galaxies, etc. We know of one kilonova. And what I understand is a gravitational wave detection of such an event would have such a huge area on the sky that you would need thousands of galaxies that you have to survey, but they would be faint. And this is why you have an area, when you talk about niche, where the WST would have an advance over what you are rightfully mentioning, the small and medium-sized telescopes in terms of spectroscopy.
Okay, thank you.
Thank you, Martin. You showed a very what's the plan for to sustain all the human resources that this center is going to gather in the next decade or so? Is it part of the 1.4 billion or no? If the 1.4 billion is mostly for infrastructure. So where's the money coming from to sustain all the personnel of the center?
You do have major research institutes for example, for particle physics in Germany, in Darmstadt, for example, or in Hamburg, DZA. And what has been negotiated in this process is that after the 15 years of building the facility have passed, the facility will enter in this kind of permanent funding with an annual budget of 170 million euros. That is the plan. And it's part of actually a contract. It's legal. It is not something that we think, oh, hopefully it's going to happen. It's something that we trust is happening.
That's what's going to sustain the 1,000 people you said.
Yeah. Well, whether it's exactly 1,000, nobody knows, but this is the order of magnitude. Yeah.
Any more questions? I have one concerning the WST. So how far is that from reality? I mean, what is the funding situation? How much money?
There's no project. We are at a conceptual design phase that will start. We will be involved at IIP on the fiber system and on the detector side. We are now starting to fill the work program, and it's a 3 years project. And I don't know exactly when this idea collection at ESO will start, but I guess the next 2 years there will be a call. And from that, you will have a decision-taking process of what kind of a project will be picked. And only from then on can you talk about funding. But in order to come up with trustworthy numbers for a budget, this conceptual design study is very important. Now, it is going to be costly, but the idea is that we use the technology of making mirrors like the segmented mirror telescope, the ELT, to make it, affordable with existing technology and so forth.
What about the timeline? Is it feasible to start in 2035?
Well,
I mean, more or less there.
Hand waving.
Okay.
Yeah.
Okay. Okay. If there are no more questions, let's thank Martin again for his
Thank
talk.
you very much.
And I welcome all of you to join us in the coffee break, in the scientific coffee later on.